magnetic field would go counterclockwise if we see it from the left for coil 3, for the number 3?
I'm not sure which rule you want to use and for which coil, because first we need to read this statement. It says, assume that coils in the plane, followed well in the same plane, and this solenoid wound clockwise as viewed from left. Did you use this statement? Clockwise as viewed from left. What does it mean? This is the most important.
This is how the current will go.
Exactly. Relative to
the left side.
So if you would be viewing like this, the current here in this solenoid, you see when you draw it like a picture, it's really not clear. But this is why you have to use this statement. So for this person, the current in this solenoid would travel clockwise. Now, how do you use this statement? What does it tell you?
We can find the magnetic field, the direction.
Okay, that's exactly right. That's the only way to find this magnetic field, this solenoid. Well, if you would flip, like at the point of view, if that would be us, we would look at this solenoid with electric current traveling clockwise, and in that case, how would we describe the direction of magnetic field generated by this current?
It was going into the page.
Exactly. But if we go now back to this person, how do we describe this direction of the same vector, but now from a point of view of that observer? Okay. If this person would be looking at the magnetic field inside this solenoid, what would be the direction?
Would it not be into the page?
Well, into the page
Into
is from you, is for you. This person is not looking at the page. This person is looking at the solenoid aside. So that for that person, the same arrow has a different direction. The arrow is the same, but different people look at it differently, and they have to use different description. This is for you. Right now, it goes away from you. But this solenoid, if you place it back in that picture, how would that arrow point?
Would it be to the right?
That would be to the right, because what you always kind of can imagine or even use something, if this is a solenoid and this is an arrow, if you take this solenoid and physically move, the arrow is supposed to move with the solenoid, and now it points, if it still points away from a person, it's going to point away from the person, but that person now will see it well away, but you now will see it to the right. See?
I see.
And now you can complete the whole magnetic field line. This is just a magnetic field vector, and the line, of course, is also a continuous loop like this. So what will be the direction of magnetic field vector at the location of the second loop here?
It will still go. It will be into the page. Into
Well, relative to you now watching this screen, how would it point?
to the right.
To the right, because it has to be the same, and same here, and the only difference is at the location of the third loop, right? So if you draw a vector, just a vector, not the whole line, just magnetic field vector at the location of the third loop, what should you draw?
A vector to the left.
Relative to you. Relative to this person, that would be at that person, into his eyes. But
Right.
relative to you, that's to the left.
Oh, I see.
So this is what makes these situations hard a little bit,
Can I ask a
because
question about?
just a second, because you have to keep in your mind at least two different perspectives. Yes, go ahead.
So I'm still a little confused about this, because if the coil is in the plane of the solenoid, then doesn't that mean the coil is above the solenoid?
This is the plane. A part of a screen is a plane. You have a solenoid and you have coil, coil, coil. They all belong to the same plane. One is to the right, one is to the left, and second is above solenoid, but in the same plane.
Right, so if I'm looking from the left and the solenoid is clockwise, then from my point of view, looking at the screen, the current in the solenoid is going to the right?
No. Because you have to say what the problem requires you to say. It says, if you look from the left, the current will follow the winding, the turns of the solenoid, and those are clockwise.
So then from the left, current is into the page.
No. If you look from the left, the current that travels in the solenoid is clockwise. Of course, when it leaves the solenoid, it travels in a certain direction. And we know how, because it goes from plus, then it goes like this, then it goes clockwise relative to that person, then it travels again to minus and like this. So here, for this part of a wiring here, you could say that right here, electric current points at the observer on the left. You could say that, but it doesn't matter. What matters is the direction of the current inside the solenoid, because solenoid creates magnetic field strong enough to affect all three coils, 1, 2, and 3.
Right, so the magnetic field lines that the solenoid creates, like the magnetic field lines of the solenoid itself, go into the page from the viewpoint of the left guy, right?
Relative to the person on the left, the magnetic field does point like this, yeah.
Okay, so then from that, am I using that to determine current through number 3, or am I just using the current of the solenoid to determine the current in number 3?
I don't understand the question. First of all, the general answer is you can use wherever you want to, as long as you do it right. So it does not matter. But in this situation, when you jumped in, we discussed the direction of this magnetic field in this solenoid from your point of view. This is the point of view of that person. But you now, you're not to the left, to the solenoid. You're looking straight at the whole picture. And relative to you, in this solenoid, magnetic field should
Point to the right.
Point to the right. Now, technically, you don't need anything else. All you have is a magnetic field of a solenoid inside it. Then you can continue to finish magnetic field line that travels through 3 loops. 1, 2, 3, and the magnetic field at the location of each loop follows the direction of the line. And now you can start analyzing what is happening when the switch is just closed. When the switch is closed, magnetic field goes from nothing to something. So flux increases.
Right.
And for the loop number 1 and for the loop number 2, you will not see any difference. It's going to be, well, again, relative to this person. It's going to be away from that person, then much more away, and now you can finish.
So I have a question now. So with the magnetic field, how do you know that it comes out of the page for loop 3 as opposed to going into the page?
I'm not sure what you're asking. This is the magnetic field vector generated by the solenoid. Magnetic field generated by the solenoid is everywhere, including the location of this loop. And the magnetic field vector must preserve the direction of the magnetic field line. And as we said, this is the magnetic field vector inside the solenoid, so outside it should continue and go back. That's the only way.
Right, but if the coil is in the plane of the solenoid, then it's like you see all sides of the circle representing the coil. So how do you know it comes from behind and then comes out of the coil and continues, as opposed to going into the coil first and then coming out?
Every object in this problem has a central point. This is the middle point of a solenoid. This is the middle point of a coil number 2. This is the middle point of the coil number 3. And this is the middle point of the coil number 1. This is what it means. They all lie in the same plane. But the actual orientation of each coil is perpendicular to this plane. These are loops in the solenoid. This is the loop number 1. This is the loop number 2. This is the loop number 3.
So if the coil is in the plane of the field, then the loop itself is perpendicular?
Well, this is exactly what this picture shows you. Otherwise, it wouldn't be this. Otherwise, it would be this. If you try to represent a three-dimensional object using two-dimensional surface, you have to figure out the way to do that. All the turns of a solenoid are perpendicular to this plane. Each loop is perpendicular, but as objects, they all belong to the same plane. So
I see. So we're actually looking at the sides of a loop, right?
I'm not sure what do you mean by size of the loop. So I can see 3 loops, and I know that if I would make this setup physically in real life situation, those loops would be perpendicular to these wires, for example.
Okay. Yes, I see. I also had one more question.
This is what it means. Center. Objects have sizes, but every object has a specific point which we associate with the location of that object.
Mm-hmm.
And all those points lie in the same plane. If you would have to draw the actual representation of each loop,
it would be like this.
I see.
Does it help? I don't know, but that is why people do this.
I see. So the little ends represent that you're looking at a coil that's perpendicular to the plane, or a loop that's perpendicular to the plane.
Yeah.
Okay, I see. I do have another question for practice 1, number 39.
Just a second. There was another student. Did she leave?
No, I'm still here.
Okay. So technically we didn't finish your problem, so you should go first. So,
Oh, yeah.
Sorry about that.
Oh, no worries.
what we have,
I think I understood what happened.
okay. Yeah, this is the magnetic field of that solenoid that travels at different loops in these directions. And let's say you're looking like this, and you only closed the switch. In that case,
Mhm.
again, relative to this person, the picture would look like this. And the last picture should demonstrate what would be the direction of the induced magnetic field,
Coming at us.
because you want to slow down the change. And for this situation, for the induced magnetic field, your
Counterclockwise.
direction is counterclockwise, but not relative to you, technically relative to that person. That's what that
Oh.
person would see. You need to kind of split your mind when it's you and when it's that person.
Mm-hmm. It's sometimes hard to.
Well, that's
Figure it
just
out.
requires practice, nothing else.
Uh-huh.
And now, of course, you could analyze loop number 2, loop number 3. What would be the difference for 3? The direction. The direction would have been now at that person, and then even more and even more. So to compensate, that would give you the induced magnetic field, well, relative to you into the screen, relative to that person, away from that person,
Mm-hmm.
which would make it clockwise for that person. Okay?
Mm-hmm.
All right.
I also had a very good question for 31.
31. 31.
It was about transformers. And like to my understanding, we have two, like one primary and one secondary. But
So someone asked about this problem on Piazza Part C, and I said, ignore it.
but do we
Part
not
A,
have
Part B,
transformers?
those are standard. This is what we've learned. Anything else beyond that, we didn't talk about it. So, because, well, idea is kind of clear, because you have different voltage, you should have different current, and power equals current squared times resistance. So you could derive what you need for Part C from that, but we don't do that,
Okay. Well, thank you.
of course.
I will stay to listen to 39, if that's okay.
Yeah, sure. So for number 39,
39. 39. 39.
I
Okay,
understand part A. It's just part B that I'm confused about because I don't understand why I'm using the external magnetic field as opposed to the induced magnetic field, like we would when we're doing, like we have 4 wires connected in a square and we want to find the net force on one of the wires.
so we are referring here for the second location of the loops. So when the loop is entering, well, I don't really need the whole thing. Okay, entering. When the loop is entering, this is just a little bit tricky. Oh. Technically, this part is also outside of our scope. I mentioned it, but it's, oops, what happened?
So I guess the base of my question is
Okay.
when we are doing net force and we're dealing with wires, we use the magnetic field that's external to the actual wire, that's our point of view, but we use the current of the wire itself, right?
Again, we use what we have to use as long as we use it correctly. I just want to check magnetic field points out of the screen. And so let's say this loop is entering the magnetic field. So right now we have only a small flux. When the loop enters more, the flux has a larger value. So to compensate this increase, the induced magnetic field should point opposite to the external magnetic field.
Yes.
Now, we don't really talk about current at this point. What we talk about magnets, because the easiest way would be now to turn the whole picture, look at it from a point of view of a person, who can see actual vectors. So let's say there is an observer on the right. That observer would not see any loops, but that observer would see two vectors. Vector that represents external magnetic field and a vector that represents induced magnetic field.
Yes.
And for that person, that would be directions left and right. So that's what I want to draw. The external magnetic field for that person. And the induced magnetic field relative to that person as well.
Mm-hmm.
And now we can go back to the beginning. When we defined magnetic field, we said the direction of the magnetic field, by definition, points from south to north inside the magnet.
Mm-hmm.
So basically what you see here now is two magnets, which is above, which is below. So we need to take a look at the poles to figure out if they attract or repel each other. And what's the question actually? What is the direction of magnetic force, or the direction of magnetic force?
So the way I ended up doing
Yeah, I wouldn't even have to do that. I could just take a look at a part of this loop. Every loop we could break down into parts that experience force according to right-hand rule. So magnetic field points out, electric current points there. So I will have force down here, but I will have force up there, and these forces cancel each other out. On this side, there is no force. On this side, there will be force.
I think the current points down.
The wrong direction for the current, yes. The current.
So you use the current of the loop but the magnetic field external, right? Not induced.
The induced magnetic field will never be as strong as the external.
I see. Okay. Okay, that makes sense.
Yeah. So
This is
okay.
what
I missed. I missed this arrow here. This will be for induced current. This is induced field, and this is induced current.
Okay,
Yes.
I see. Yes, that makes sense.
Well, of
and-
course, if the net magnetic field affects the external and the induced, but in magnitudes, the induced will never be as strong as the external.
Okay, I see. And then I just have one more general question. So
Yes.
in lecture 16, we were given the wave equations to be a sine or cosine times omega t minus kx.
Just
But then
a
it's
second, I just want to finish because I don't know, it makes sense to me. You see, if you would be entering this loop like that, it would be acting like this magnet. So basically, you would have two magnets repelling each other. So that is why the force from magnetic field also kind of should point to the left. See? North and north should repel each other. This is the magnet that represents the loop that is entering. And this is the magnet that represents the external field, and they repel, so the force should point like that.
To be honest, I didn't understand that, but I understood the other way that you did it with the right hand rule.
Well, two magnets with identical like poles facing each other, they should repel each other. So when this loop starts entering this magnetic field, the external magnetic field, well, it is generated by something, so it could be represented by a magnet. And
But the magnet is representing an external magnetic field.
Yeah, and there is a magnet that represents the induced magnetic field, and those kind of face each other with the
Yeah.
same poles, so they try to repel each other.
Okay, and then when you bring a north pole close to a coil, the coil's current will be clockwise, but then the induced current will be counterclockwise.
That requires more specific analysis. What moves in what direction, so we could talk about that as well. But I just want to, again, say
Yeah.
that no matter how we approach it, we should observe at the force acting like a resistance,
Mhm.
Like the external magnetic field resists
Mhm.
the entrance of this coil.
Okay.
Yes.
Does it matter what's doing the movement, whether it's the coil or the magnet?
No.
Okay, just wanted to
Yeah.
make sure.
Motion is relative. We could select the location of an observer anywhere, put it
Okay.
on a coil. That would make analysis harder, but physics can depend on how we look at it, so.
Right. Okay, so then my other question is just, I'm a little confused about why we switched the placing of terms in the wave function, because in lecture 16 it was a cosine or sine times the quantity of mu times t minus k times x. But then in lecture 17, we switched it so that it was a sine or cosine times the quantity of kx minus mu naught. And I just want to, I just don't understand how they're both the same or why we switched them.
Well, first of all, as you said, sine or cosine,
Yes.
it means it doesn't really matter because they all are, well, interchangeable.
Right.
And that also includes what do you do inside? It's mathematically, practically identical if you write it like this.
Mhm.
Kx minus this, but
Mhm.
that would add a minus in front of it. So it's basically again replacing one function with a similar function. It does not matter as long as we apply it correctly for that
So the
specific
only-
situation.
Sorry. So the only way that the top equation can be equal to the net to the lower equation is if you add a minus sign in front of a.
Well, you have to go to trigonometry. Sine of negative alpha equals negative sine of alpha.
Okay.
That's one.
So then my question following that is, we used a sine of kx minus mu t without the negative in front of the a when we derived the equation for a standing wave.
So what?
So if we drop the negative in front of the a, doesn't that affect
We
the
had we had a situation with two waves traveling
Yes.
toward each other. Then we said, okay, for one wave we use this equation. A times sine, I don't really remember how was it, this way or another way, it doesn't matter.
So, okay, so when you say it doesn't matter, here's the thing though. When we added the two equations, or technically subtracted them, and we used like the trig function that was like, I think it was sine of alpha plus beta gives me 2 sine alpha beta cosine, no, sine,
Again, it doesn't matter. Let's,
But
so if
when
you,
when
let's
I
say,
derived the way that we did it in class, but using the reverse, like using this equation, what you wrote, because in class we did kx minus wt. When I did it the other way, using this original equation, my terms with cosine and sine flipped.
maybe, that,
So
that means you got a different standing wave. So if you would start from this, so we've got two choices, simple choices. In reality, we got many more choices because it could have been sine and cosine or whatever combinations.
Right.
So every time you just have to apply the exact relationship from trigonometry if you want to. You don't have to. But if you want to, you can. But you have to remember that for each wave traveling in one direction, we have to use the wave traveling in opposite direction.
Right, and they just change the plus or minus for that.
And for that inside, yeah. But inside of what? Inside of, I think here you should do negative kx minus omega t. So
it's always the kx that flips. Because
yes.
I think there was a WebAssign problem.
It is always kx that changes the direction. And now, if you do the math, well, this will be negative a times sine, and you flip these. And this will be negative a times sine, and you just do this.
I see, okay. So we would always have to be either given the standing wave equation or one of the two wave equations to know what kind of like trigonometry it is, right? Like if like I can't just get a graph or something and just assume that it's wt minus x minus kx as opposed to kx minus omega t, right?
Well, again, that depends, because if you can see how it changes, I don't know, with time at one place and how it changes, let's say the same. at a certain time, you could extract the information about the exact
So how would I do
equation if you would have to. You don't have to. Well,
that? Okay.
all right. First of all, if you look at this, usually it's like this. At x equals 0, you know how it changes with time, and at initial at time, you know how it changes in space.
Mhm.
So in this case, you would have to combine kind of two signs. So it should be a sign plus or minus omega t plus or minus kx.
I see. Okay, because both functions are sine. So you
Yeah.
would have,
If
and
you,
that equation is equal to a sine omega t sine kx.
no, this represents only one traveling wave. This wave travels, and how does it travel? Well, if we set time to 0, we should get just a standard sign for the position, so we cannot use
I see.
minus. But if we set x to 0, we should get a standard sign for time. So this actually will be a wave described by this equation. This is the only way to fit both pictures, but this plus tells us that actual wave should travel to the left in this situation. It doesn't end there. It's everywhere.
But why is it to the left? Because in class we said that. Oh no, sorry, my apologies. Yes, that's
Yes.
correct.
So we don't know exactly from the graph. We don't know exactly what is happening until we finish our analysis, and we will find an equation that fits both graphs.
Right.
And then we could extract that information just by looking at this.
Okay, I see. I do have one more question. And it's homework part 4, question 1. Oh, also, while you're pulling it up, for waves and like the sine and cosine and all that stuff, our calculators have to be in radians, right?
It is your calculator. You can set it to anything you want to. But when you need to calculate sine or cosine of something, well, if you use radians, the calculator should be in radians. If you use degrees, the calculator should be in degrees.
Okay, because I had it originally in degrees, but then I had trouble with one of the problems, and one of my classmates was like, you need to put it in radians. So that's really where the base of that question is coming from.
Well, that's a very common mistake.
Yeah.
This was problem from part 3, I think.
Part 4. Oh, sorry. So the question I'm asking about is in part 4.
Oh, in part 4. Okay, part
Sorry.
4. But there was a question about standing waves and traveling waves. I don't see. No, pulses. What did it? Homework 2, part 4. Open. Oh, this is the right one. This is question number 3. This is basically when you have to make sure you're using radians, because you have to use International System of Units for all your calculations here.
Yes.
Okay. So
Okay.
what's your problem number
Question 1.
1?
Yeah. So I reviewed it with my TA, and we had established like a method to go with, and it was you would use the omega formula, you would use velocity over time to get displacement, and we just used a bunch of mini equations to get the right answer. But when I used that method, I wasn't getting the right answer, and the only method that I could get the right answer with is if I did time is equal to n times period, and then I went further down where n was equal to capital D over lowercase d naught, but can we try to go over it using like our equations as opposed to
I don't know
time?
what you have here. Let's analyze. First, we have a string and a wave travels, doesn't matter in which direction, let's say to the right. And you know the amplitude of the wave is equal to 2 point, well, you may have a different number. You know the wavelength is equal to a given number, and the speed, which is equal to frequency times wavelength, gives you frequency or period. So you can calculate frequency as this, or you can calculate period as this, and that will give you a number for the period. So these are preparations, you know. Amplitude and the period. Everything else is irrelevant anymore. Displacement. How much time will it take to travel this displacement? Today I solved the opposite problem. When we know time, and we were looking for displacement. Of course, it should work both ways. So, what we know is that, actually I want to ask you, if you wait exactly one period, what will be the distance traveled by this point?
If you went exactly one period?
Yes.
So period is equal to 1 over frequency, and frequency is equal to velocity over weight, or yes,
No,
velocity.
that's not the way to think about it.
So you would travel one wavelength, right?
The wave travels one wavelength as a wave, but that's not what we're looking for. We are cutting the wave out, and we're looking at the motion of a single point right here. That single point, like a ball on a spring, moves up and down, up and down. So moves up and down, up and down, up and down. That is simple harmonic motion. And the question is, what's the distance traveled by this point in one period?
So it would be twice the amplitude, because it would go down to the other side and then come back up, which is not twice the amplitude, that's 4 times the amplitude.
Exactly. So it's one amplitude to the equilibrium, another, second, the third, fourth amplitude. So
Yes.
distance traveled in one period is equal to 4 amplitudes.
Okay, I see.
So now, your distance is equal to 1.5 kilometers. So, how, if you know, what do I want to ask? I want to ask you this. How many periods should it move up and down to travel this whole distance if you know that in one period it travels 4 amplitudes?
So in one period it travels 4 amplitudes, and I'm trying to relate that to the horizontal distance. So I would
there is nothing horizontal here. This is a transverse displacement. Transverse displacement. So this point, which you're looking at, moves up and down, 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 up and down. I can do it for a long time, but eventually total distance traveled is equal to 1.5 kilometers.
Oh, I see. Okay, so I would do 1.5 kilometers divided by 4 amplitudes.
That would give you that number of periods.
And then I can use the equation T equals number of periods times period.
And if you know number of periods, total time will be equal to this number times one period.
Mm-hmm.
That's how it should work.
I see. Okay. Is it times or divisible?
This is times one period times the number of periods gives you the total time.
Mhm. Okay, I see. Yes, that makes sense. Okay. Yeah, I think what was my logic was incorrect because I was thinking about 1.5 as being horizontal as opposed to being vertical. So, okay, that makes sense now.
Well, it's right here.
Yes.
Transfers displacement to travel through total distance. Well, actually, it might have some interpretations, but
Yes.
this is what it is. Otherwise, this problem would not be solvable, I guess.
Right. Right. I do have like one other question. So one of the homework problems said that there were two frequencies measured and they were successive as opposed to consecutive. So
That
when
should be the same.
oh, it is? Okay.
Yeah. It means one frequency has been measured, and then the next frequency has been measured. The next possible by generating
I see.
successive, consecutive, next, it's all the same.
Yes. Okay, I see. Okay, thank you so much.
Of course.
Oh, as of right now, there shouldn't be a conflict for exam 2. We talked about this a while back.
Should be what?
There shouldn't. So I talked to you a while back about a conflict for exam 2.
Okay.
Yes, yeah, but as of right now, I'm set to take the exam on Monday. There shouldn't be a conflict, but if anything comes up, I'll definitely reach out.
Well, you cannot do it just before the exam.
No, absolutely not. No.
Okay.
No, I respect your time, so I'm not gonna be a headache to you. I promise.
It's not a headache. It's just time.
Yes, I definitely understand. Thank you so much.
You're welcome. Anyone else? What do we do? Okay. No, okay.